Hello and welcome. In this comprehensive lesson, we're going to dive deep into the world of ordinary differential equations, or ODEs. By the end of this video, you will be able to classify ODEs, solve several types of first-order equations, and tackle second-order equations using various powerful methods. So, what exactly is a differential equation? Simply put, it's an equation that involves an unknown function and its derivatives. For example, an equation like y prime equals 2x is a differential equation. Here, y is our unknown function, and y prime is its first derivative. The goal is to find the function y that satisfies this equation. In this simple case, we can find y by integrating both sides. Integrating y prime gives us y, and integrating 2x gives us x squared plus a constant of integration, c. So the solution is y equals x squared plus c. This is a family of solutions, and the constant c can be determined if we're given an initial condition, like y of 0 equals 5. Plugging in x equals 0 and y equals 5, we find that c must be 5. This gives us a unique solution, y equals x squared plus 5. Now let's talk about how we classify these equations. We classify them by their order and their linearity. The order of an ODE is the order of the highest derivative in the equation. For example, y prime equals 2x is a first-order ODE because the highest derivative is the first derivative. An equation like y double prime plus y equals 0 is a second-order ODE because it contains a second derivative. The second classification is linearity. An ODE is linear if the unknown function and its derivatives appear only to the first power and are not multiplied together. The coefficients can be functions of the independent variable, x. For instance, x times y prime plus y equals x squared is a linear first-order ODE. The coefficients are x and 1, which are functions of x. On the other hand, y prime equals y squared is a nonlinear ODE because the unknown function y is squared. This is a crucial distinction, as linear ODEs are generally much easier to solve. In this video, we will focus on first-order and second-order linear ODEs, as they are the most common and have well-established solution methods. Let's begin with first-order equations. Our first major topic is first-order differential equations. In this section, you will learn to solve three important types: separable, linear, and exact equations. We'll start with the simplest type, separable equations. A first-order ODE is separable if it can be written in the form dy by d, x equals a function of x times a function of y. The key idea is that we can separate the variables, putting all the y terms on one side with dy and all the x terms on the other side with dx. This gives us 1 over h of y dy equals g of x dx. Once the variables are separated, we can solve the equation by integrating both sides. Let's look at our first example. dy by dx equals x squared over y squared. This is clearly separable. We can multiply both sides by y squared to get y squared dy equals x squared dx. Now we integrate both sides. The integral of y squared dy is y cubed over 3, and the integral of x squared dx is x cubed over 3. We only need one constant of integration, c. We can simplify this by multiplying by 3, giving us y cubed equals x cubed plus 3c. Since 3c is just another arbitrary constant, we can call it c again. So, the general solution is y cubed equals x cubed plus c. We can also solve for y to get y equals the cube root of x cubed plus c. Let's try a second example. Suppose we have dy by d x equals 2x times y. To separate the variables, we divide by y and multiply by dx. This gives us 1 over y dy equals 2x dx. Integrating both sides, we get the natural log of the absolute value of y on the left and x squared plus c on the right. To solve for y, we exponentiate both sides using the base e. This gives us the absolute value of y equals e to the power of x squared plus c. Using exponent rules, this is e to the x squared times e to the c. Since e to the c is just a positive constant, we can replace it with a new constant, a. Removing the absolute value sign means a can be positive or negative. So, The general solution is y equals a times e to the x squared. Finally, let's look at a practice problem. Solve dy y dx equals y squared plus 1. Pause the video here and try to solve it yourself. Welcome back. Let's solve it together. We separate the variables to get 1 over y squared plus 1 dy equals dx. Integrating both sides, the left side is the integral of 1 over y squared plus 1, which is the inverse tangent of y. The right side is the integral of 1, which is x. Don't forget the constant c. Solving for y, we get y equals the tangent of x plus c, and that's our solution. We have now successfully solved several separable equations. Next up are linear first-order differential equations. In this scene, you will learn to identify and solve these equations using a powerful technique called the integrating factor method. A first-order ODE is linear if it can be written in the standard form, dy by dx plus p of x times y equals q of x. The key to solving these is to find an integrating factor, which is a function that, when multiplied by the entire equation, makes the left side the derivative of a product. The integrating factor, which we'll call mu of x, is given by the formula e to the power of the integral of p of x dx. Let's see this in action with an example. Solve dy flies d x plus 2y equals 6. First, we identify p of x and q of x. Here, p of x is 2 and q of x is 6. Now we find the integrating factor. Mu of x equals e to the integral of 2 dx, which is e to the 2x. We don't need a constant of integration here. Next, we multiply the entire standard form equation by our integrating factor, e to the 2x. This gives us e to the 2x dy by dx plus 2e to the 2xy equals 6e to the 2x. The magic happens on the left side. Notice that it's the result of the product rule for differentiation. The derivative of the product y times e to the 2x is y prime e to the 2x plus y times 2e to the 2x. This is exactly what we have on the left. So we can rewrite the equation as the derivative of y times e to the 2x equals 6e to the 2x. Now we integrate both sides with respect to x. The integral of derivative just gives us the original function, y times e to the 2x. The integral of 6e to the 2x is 3e to the 2x. And we add our constant of integration, c. Finally, we solve for y by dividing by e to the 2x. This gives us y equals 3 plus c times e to the negative 2x. This is the general solution. Let's try a practice problem. Solve x dy by d, x plus y equals x squared. First, we must put it in standard form by dividing by x. This gives us dy by d, x plus 1 over x times y equals x. Now, pause the video and try to solve it using the integrating factor method. Welcome back. Let's solve it. P of x is 1 over x. The integrating factor is e to the integral of 1 over x dx, which is e to the natural log of x, or simply x. Multiply the standard form equation by x. This gives us x dy by d, x plus y equals x squared. The left side is the derivative of xy. So we have the derivative of xy equals x squared. Integrating both sides gives xy equals x cubed over 3 plus c. Finally, dividing by x, we get the solution y equals x squared over 3 plus c over x. We have now mastered the integrating factor method for linear first-order ODEs. Our final type of first-order equation is the exact equation. In this scene, you will learn how to test for exactness and solve these equations. An exact equation is one that can be written in the form m of x, y dx plus n of x, y dy equals 0. The key idea is that the left side of this equation is the total differential of some function. Let's call it f of x comma y. The total differential of f is the partial derivative of f with respect to x comma dx plus the partial derivative of f with respect to y dy. If our equation is exact, then m must be the partial of f with respect to x, and n must be the partial of f with respect to y. So how do we test for exactness? We use a simple condition. An equation is exact if and only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. This is the exactness test. Let's work through an example. Solve 2xy dx plus x squared plus 1 dy equals 0. First we identify m and n. M is 2xy and n is x squared plus 1. Now let's perform the exactness test. The partial derivative of m with respect to y is 2x. The partial derivative of n with respect to x is also 2x. Since they are equal, the equation is exact. Now we need to find the function f. We know that the partial of f with respect to x is m, which is 2xy. To find f, we integrate m with respect to x. The integral of 2xy dx is x squared y. Since we're integrating with respect to x, the constant of integration can be a function of y, which we'll call g of y. Next, we use the fact that the partial of f with respect to y is n. We differentiate our expression for f with respect to y. The partial of f with respect to y is x squared plus g prime of y. We set this equal to n, which is x squared plus 1. The x squared terms cancel out, leaving us with g prime of y equals 1. Integrating with respect to y, we find that g of y equals y. Now we substitute g of y back into our expression for f. This gives us f of x comma y equals x squared y plus y. The solution to an exact equation is simply f of x comma y equals a constant, c. What if the equation is not exact? Sometimes we can make it exact by multiplying by an integrating factor. This is a more advanced topic, but the idea is to find a function mu of x or mu of y that makes the new equation exact. For example, if the expression partial differential m slash partial differential y partial differential n slash partial differential x divided by n is a function of x only, say h of x, then the integrating factor is e to the integral of h of x dx. Similarly, if the expression partial differential n slash partial differential x partial differential m slash partial differential y divided by m is a function of y only, say k of y, then the integrating factor is e to the integral of k of y dy. Let's try a practice problem. Solve 3x squared y plus 2 dx plus x cubed dy equals 0. Pause the video and first test for exactness. If it's exact, solve it. If not, see if you can find an integrating factor. Welcome back. Let's check for exactness. M is 3x squared y plus 2, and n is x cubed. The partial of m with respect to y is 3x squared. The partial of n with respect to x is also 3x squared. They are equal, so the equation is exact. Now let's find f. We can integrate m with respect to x, or n with respect to y. Integrating n is simpler. F of x comma y equals the integral of n dy, which is the integral of x cubed dy. This gives us x cubed y plus a function of x comma h of x. Now we differentiate f with respect to x and set it equal to m. The partial of f with respect to x is 3x squared y plus h prime of x. Setting this equal to m, we get 3x squared y plus h prime of x equals 3x squared y plus 2. The 3x squared y terms cancel, leaving h prime of x equals 2. Integrating with respect to x gives h of x equals 2x. Substituting h of x back into f, we get f of x, y equals x cubed y plus 2x. The solution is f of x comma y equals c, so x cubed y plus 2x equals c. We have now covered the three main types of first-order ODEs. Now we move on to our second major topic, second-order linear homogeneous differential equations with constant coefficients. In this scene, you will learn how to solve these equations by finding the roots of a characteristic equation. A second-order linear homogeneous ODE with constant coefficients has the form ay double prime plus by prime plus cy equals 0, where a, b, and c are constants. The key to solving these is to guess the solution of the form y equals e to the rx. Let's see why. If y equals e to the rx, then its derivatives are y prime equals re to the rx, and y double prime equals r squared e to the rx. Substituting these into the ODE, we get a times r squared e to the rx, plus b times re to the rx, plus c times e to the rx, all equals 0. We can factor out e to the rx, which is never 0. This leaves us with a times r squared, plus b times r plus c equals 0. This is a quadratic equation in R, and we call it the characteristic equation. The solutions to the ODE depend entirely on the roots of this characteristic equation. There are 3 cases. Case 1. 2 distinct real roots. If the discriminant b squared minus 4ac is positive, we get 2 different real roots, r1 and r2. The general solution is a linear combination of the 2 fundamental solutions, e to the r1x and e to the r2x. Let's solve an example. Y double prime plus 5y prime plus 6y equals 0. The characteristic equation is r squared plus 5r plus 6 equals 0. Factoring this, we get r plus 2 times r plus 3 equals 0. The roots are r1 equals negative 2 and r2 equals negative 3. Since we have 2 distinct real roots, the general solution is y equals c1 e to the negative 2x plus c2 e to the negative 3x. Case 2. A repeated real root. If the discriminant is 0, we get only one real root, r. The general solution is y equals c1 e to the rx plus c2x e to the rx. Notice the extra factor of x in the second term. Let's solve y double prime minus 4y prime plus 4y equals 0. The characteristic equation is r squared minus 4r plus 4 equals 0. This is a perfect square. R minus 2 squared equals 0. So we have a repeated root, r equals 2. Using the formula for repeated roots, the general solution is y equals c1 e to the 2x plus c2x e to the 2x. Case 3. Complex conjugate roots. If the discriminant is negative, we get 2 complex conjugate roots of the form alpha plus or minus I beta. The general solution is y equals e to the alpha x times c1 cosine of beta x plus c2 sine of beta x. Let's solve y double prime plus 4y equals 0. The characteristic equation is r squared plus 4 equals 0. This gives r squared equals negative 4, so r equals plus or minus 2i. Here, alpha is 0 and beta is 2. Plugging these into the formula, we get y equals e to the 0x times c1 cosine of 2x plus c2 sine of 2x. Since e to the 0x is 1, the solution is y equals c1 cosine of 2x plus c2 sine of 2x. Let's try a practice problem. Solve y double prime minus 2y prime plus 5y equals 0. Pause the video and find the roots of the characteristic equation. Then, write down the general solution. Welcome back. The characteristic equation is r squared minus 2r plus 5 equals 0. This doesn't factor easily, so we use the quadratic formula. R equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Plugging in a equals 1, b equals negative 2, and c equals 5, we get r equals 1 plus or minus 2i. Here, alpha is 1 and beta is 2. The general solution is y equals e to the x times c1 cosine of 2x plus c2 sine of 2x. We have now covered all 3 cases for solving second-order homogeneous ODEs. Finally, let's tackle second-order linear, non-homogeneous differential equations. In this scene, you will learn how to solve these equations using the method of undetermined coefficients. A non-homogeneous equation has the form ay double prime plus by prime plus cy equals f of x, where f of x is a non-zero function. The general solution to a non-homogeneous equation is the sum of 2 parts. The general solution, y, equals the homogeneous solution, y sub h, plus a particular solution, y sub p. The homogeneous solution, y sub h, is the solution to the associated homogeneous equation, which we find by setting f of x to 0. We just learned how to do this in the previous scene. The particular solution, y sub p, is any single solution to the non-homogeneous equation. The method of undetermined coefficients is a way to find this particular solution. The method works by making an educated guess for the form of y sub p, based on the form of f of x. Here are the common cases. If f of x is a polynomial, we guess a polynomial of the same degree. If f of x is an exponential, we guess an exponential. If f of x is a sine or cosine, we guess a combination of both. Let's solve an example. Y double prime minus 3, y prime minus 4, y equals 3e to the 2x. Step 1. Find the homogeneous solution, y sub h. The characteristic equation is r squared minus 3, r minus 4 equals 0. Factoring gives r minus 4, r plus 1 equals 0. So the roots are 4 and negative 1. So the homogeneous solution is y sub h equals c1 e to the 4x plus c2 e to the negative x. Step 2. Find the particular solution, y sub h. Since f of x is 3 e to the 2x, our guess for y sub p is a e to the 2x. We need to find the derivatives of our guess. Y sub p prime is 2ae to the 2x, and y sub p double prime is 4ae to the 2x. Now we substitute these into the original non-homogeneous equation. This gives us 4ae to the 2x minus 3 times 2 ae to the 2x minus 4 times ae to the 2x equals 3e to the 2x. Simplifying the left side, we get negative 6ae to the 2x equals 3e to the 2x. Dividing by e to the 2x, we find that negative 6a equals 3, so a equals negative 1/2. Our particular solution is y sub p equals negative 1/2 e to the 2x. Step 3. Write the general solution. The general solution is the sum of y sub h and y sub h. So y equals c1 e to the 4x plus c2 e to the negative x minus 1/2 e to the 2x. There's a special case called the rule of modification. If your initial guess for y sub p is already part of the homogeneous solution, you must multiply your guess by x. For example, if f of x is e to the 4x and e to the 4x is already in y sub h, your guess for y sub p should be ax e to the 4x. Let's try a practice problem. Solve y double prime plus y equals 2 cosine of x. Pause the video and try to solve this one, paying close attention to the rule of modification. Welcome back. First, the homogeneous solution. The characteristic equation is r squared plus 1 equals 0, so r equals plus or minus I. This gives y sub h equals c1 cosine of x plus c2 sine of x. Now for y sub h. Our initial guess for f of x equals 2 cosine of x would be a cosine of x plus b sine of x. But notice that this guess is identical to y sub h, so we must apply the rule of modification and multiply by x. Our new guess is y sub p equals ax cosine of x plus b x sine of x. This is the correct form to use. Now we find the derivatives. This requires the product rule. Y sub p prime is a cosine of x minus ax sine of x plus b sine of x plus bx cosine of x. Y sub p double prime is negative 2 a sine of x minus ax cosine of x plus 2b cosine of x minus bx sine of x. Substitute these into the original equation. Y double prime plus y equals 2 cosine of x. The x cosine of x and x sine of x terms cancel out, leaving us with negative 2a sine of x plus 2b cosine of x equals 2 cosine of x. By comparing the coefficients of sine and cosine on both sides, we get a system of equations. The coefficient of sine on the left is negative 2a, and on the right it's 0, so a equals 0. The coefficient of cosine on the left is 2b, and on the right it's 2, so b equals 1. Our particular solution is y sub p equals x sine of x. The general solution is y equals c1 cosine of x plus c2 sine of x plus x sine of x. Let's quickly recap what we've learned today. We've covered a lot of ground in the world of ordinary differential equations. We started with first-order equations, learning how to solve separable, linear, and exact types. We saw how to test for exactness and how to use integrating factors. Then, we moved to second-order homogeneous equations with constant coefficients. We learned to solve them by finding the roots of the characteristic equation, handling distinct real, repeated real, and complex conjugate roots. Finally, we tackled second-order non-homogeneous equations using the method of undetermined coefficients. We learned to find the general solution as the sum of the homogeneous and particular solutions, and we saw the importance of the rule of modification. You are now equipped with a powerful set of tools to solve many common types of ordinary differential equations. The key is to first classify the equation and then apply the appropriate method. Thank you for watching. Keep practicing, and you'll master these techniques in no time.